Welcome back to our lesson through linear algebra, and we are at null space or the kernel and range of a linear transformation. Okay, so let's dive deep into this together. Okay, so the null space and range of a linear transformation, what is the definition? Let V and W be vector spaces T such that V maps to W. So you take an element in V, you do something to the V, and then it will give you an element in W. Be a linear transformation, then the null space or the kernel of T is defined as capital N of T is the set of all vectors. So just understand all these symbols here. This curly braces you have here means the set, right? So these are the elements or the members of that set in V, such that if you take the transformation of X, you will get 0. So you want to get all the elements in V such that when you perform T on X, you're going to get 0, right? The definition or how you do the perform, how you perform the operation by T will be given in any problem, okay? All right. Whereas the range or the image of T is defined to be R of T, and this R of T is defined to be the values you get when you transform X. So the transformation of X such that X belongs to V. So what this means is when you transform X, what do you get, right? So you want to get all the set of all the vectors or all the results you will get when you transform all the X's in V. Okay, and remember, the null space is a subset of the vector space you start with, the V, and then the range or the image of T is a subset of the other side. So this is a mapping, right? You are mapping something from V to W. You can call this to be the domain and the other one to be the codomain, right? And we are saying the null space is a subset of the domain, and then the range is a subset of the codomain. All right, that's what we want to say. All right, let's pick some general examples of these linear transformation and find their kernel or their null space and the range. Okay, so let V be V and W be vector spaces, and let T be such that V maps to V. So you take an element in V, map to the same V. It will give you an element back in V. All right, and T0 or T0 be defined as V maps to W, be the identity and 0 transformations respectively. So what this means is that this first transformation here, this first transformation here corresponds to the identity transformation, and then this second one corresponds to the 0 transformation, right? So the identity transformation, what does it say? So we're going to first of all dive into the identity transformation, which is the T such that V maps to V. The identity transformation, some books will call it I for identity. It means if I pick an X, which is a vector in V, and take the transformation of X, I get X back, right? That's the identity. Whatever you perform on the X, you get the same X back, right? So that's the definition of the identity transformation. And then the 0 transformation is also defined to be such that V maps to W. What it means is that when you pick any X in V, right? X is a vector, okay? That's why I have the arrow there. You can put an arrow or a bar. It will give you the 0 vector in W. Remember, this definition is very important. What you are doing is when you take the transformation of X, you're going to get the 0 transformation or the 0 vector in W. That is why we have the sub W here, right? The subscript W. So what I mean by here is that you want all the vectors, whatever transformation you do, whatever you do on all the vectors in V, you're going to get a 0. That's what this transformation means. The 0 transformation means it takes an element in V and maps it to the 0 vector in W. Okay, so now let's come back to answer all these ones, right? The A part is saying that we should find the null space or the kernel of this identity transformation. So the first thing is we understand that the transformation for identity transformation, or the operation or the definition of the identity transformation, is that it takes an element in V and maps it to the same element. When it perform, or when it acts on an element or a vector X in V, it gives you the same X. And the question is, what are some of the vectors in V that this transformation, so want the vector such that, so this is equal to all X in V such that the transformation of this X is going to give us 0. And what are some of the X's that will happen this way, or that will give us this definition? Remember, the identity transformation is just for taking an element and giving the element back. And the only thing that happens to give us 0 is only when, so the identity transformation, if this is going to give us 0, that is a 0 vector, then this is only possible if, that is if and only if X is equal to 0. Why? Because it takes an element and give us the same thing. So if X is not 0, imagine X is not equal to 0, then the transformation of X will be equal to X, which is not equal to 0. But we want to get a 0 vector, right? So this will only happen for the identity transformation. Remember, you need to be very careful about the transformation or the definition of the transformation. So when X is 0, then indeed you're going to have the transformation to be equal to 0, because the transformation will give you the same thing you put. The input you put in, you get the same thing out as an output. Okay, so here if your input is 0, your output will be 0, because it says you get the same input as the output. Okay, so here the null space will be equal to just the 0 vector. All right, so that is it. Now on the identity transformation, what is the range? What is the range of the identity transformation? Remember, whatever element you pick in V, right, the transformation of that element will give you the same thing back. Where does this element lives? It lives in V, right? So it means all the output you get will still be part of V, or will still belong to V. So it means that the range of the identity transformation is still the same inputs, right? The range is the output you get from this transformation, so the range is still going to be the same V, the vector space V. Okay, now let's go to the 0 transformation. Right, now I want to find the null space of the 0 transformation. Remember, the null space of the 0 transformation is defined to be whatever X you pick, when you take the transformation, you should get 0. That's what it means. There's 0 in the W, or you can, some people don't write it that way, but you can leave it like that. Okay, you can leave it as 0 or 0 in W. Let me just make it just 0. Okay, so it doesn't matter here, it doesn't matter which X you pick. So it means that every X you pick will give us 0. That's a 0 transform. It transforms all vectors to 0. So what is the null space? Right, the null space is you want all the vectors in X, right, sorry, vectors in V, such that now the 0 transformation of the X will give us 0. But the question is, what is the definition of this transformation? It's saying that it will take every X, no matter which the X is, or no matter what the X is, and give us 0. So it means the null space is actually the whole V, because every V it picks, or every element it picks in V, it gives us a 0 transformation, right? That's the null space. Now the range of the 0 transformation, what is it? What does this give us whenever we take the transformation? Whenever we take the transformation, it gives us 0, and this 0 belongs to W. So the range is only the 0 vector, because the output is always 0. That's what we get. All right, and the output is the range. All right, I hope you like the lesson. In the next discussion, I'm going to pick a very insightful example that do not use these transformation, and give us a basic or a specific the transformation, and then we'll have to go through it and deduce the null space and the range of the image. All right, see you in our next discussion. Like, comment, and share. So okay.